All right, hello there. Okay, so I just have a few slides to go through and then we'll get into the tool itself, but I just want to set the stage so we're all comfortable with what we're talking about here. So first off, I wanted to go through the HyperLynx family. There's a number of tools that make up HyperLynx. Originally, HyperLynx started out as just the signal integrity tool, but we've grown it over the last many years, and it covers a lot of the high-speed verification space, including power integrity, DRC rules in the EMI space, and the safety, and also power and SI checking. And then we've got full wave solvers for your extremely high-speed designs to get accurate via models and other structures for these multi 10s or 20 gigahertz space. And then there's also thermal analysis, again, to help augment that high-speed verification environment. So just quickly to go through the different tools that we have in the signal integrity space, there is LineSim, which is a pre-layout environment where you come through and build up your constraints for layout. So how long should your traces be? What sort of termination can you use? What kind of via structures are going to work out? And once you get a structure that's going to enable your signal to get from one chip to the next without any issues, then you can go ahead and use those constraints to drive the layout. And then the next step is to bring that layout back into HyperLynx in board sim and test the laid out board, the traces that are actually there, and see if they are doing what you intended them to, and just verify at the end that your signal integrity is still intact. This covers the original traditional signal integrity space, just looking at noise, crosstalk, and timing. We have additional tools to help out with DDR-X design. These are wizards which will go through and get your time of flight information and compare it against JEDEC standards and let you know whether your timing on your DDR buses are adequate or not. And then we have additional tools for the SERDES space, so these extremely high-speed differential interconnects, and there's a number of tools in that space, and that's where we're going to be focusing today, really, is what we have in there to help out that flow. On the power integrity side, we have tools to help out with the DC drop analysis. So if all your chips were pulling maximum power, what would the voltage levels be across a particular power plane, or what would the current density be across that same power plane? That's the first part of the question. And then the second part is the AC power plane analysis, where we're looking at your capacitors, the capacitance of the stack up, the way the capacitors are mounted, their locations and values, and trying to figure out whether all of that is doing its job or not, or whether additional capacitor values are needed or the locations need to be changed. So it helps you analyze that particular problem. The DRC tool, this is a little bit different approach to the signal integrity, EMI, and power integrity space. Instead of analyzing the boards, we just look for structures that cause problems, and it's specifically designed to do that. So just quickly as an example, here in this picture, we've got a trace that crosses a gap and does that a few times. If this is a high-speed trace, that's going to be a big impedance change, not only for the signal trace, but the return path. And between those two, we're going to get a lot of radiation. It basically becomes an antenna there. And so we just highlight that that's not a good thing to do, and then you can go reroute that so that you don't have that problem. So just as an example of some of the things we can look at in the SI space, we can look at your differential pairs, making sure that they are balanced. Several other things we can check about those. There's also a number of rules that focus more on DDR type routing. So that's just in the SI space, lots of different things we can check for. The power integrity space, this is focusing more on the capacitors and the vias, the things that make up the power plane, checking to make sure that some basic structures are there and capacitors are placed the way you want them to. So these are things that typically people can stare at the Gerbers for a while and find these kind of things, but it's a good chance you'll miss stuff. So we just automate that process of looking over the Gerbers and finding all this for you real quickly. Here's the EMI stuff, which is where this tool originated, focusing on looking for nets crossing gaps, as we mentioned. But there's other things like metal islands and IO coupling and other structures that can cause EMI, and we can find those for you so that you can remove them from the design. And then if you do find things as you're going through these, there's always the option to go through back to HyperLynx SI or PI and do actual analysis to figure out whether the things flagged in the DRC tool actually are issues that you want to or need to fix. A new thing to this flow is safety rules, and this covers things like creepage and clearance for high voltage nets. So that's a big issue there, trying to verify that you're not going to accidentally short out two connections through creepage. So, and then we've got a couple rules now in the analog space. So that's the HyperLynx DRC tool. The advanced solvers, I mentioned they're the full 3D filled solvers. So this picture down here is looking at board sim, but you know, the board sim trace itself is pretty good, but I get to these little structures where, you know, that I'm going through the board, there's vias, there's ground plane stitching vias to try and help with the impedance. At 10 gigahertz, 20 gigahertz, these things become an issue. At lower frequencies, I could ignore this structure, but at those higher frequencies, I really need to get a good model of that. So we have integrated ways within HyperLynx Board Sim to easily generate 3D EMI models or field solve models there of those structures that actually come back in S parameter format, and we'll go over some of that today. But again, and actually that's a lot of the focus today is seeing how these structures play into the analysis of these high-speed differential nets. The last item is kind of new to this, to our tools. This is a power aware analysis. We've had tools that kind of danced all around this, but now we've got a fully integrated power analysis tool to deal with particularly high-speed buses. So this comes into play with DDR4 and DDR5, which is coming up, where you've got very fast nets that are all switching at the same time. They're tightly coupled, and a lot of analysis is done just kind of ignoring these items, maybe some best practices, but with DDR4, that's becoming something that you can't really do without some sort of simulation. So this will incorporate HyperLynx SI as well as the HyperLynx PI, the power integrity, so that we can get the power plane and how it's going to react to multiple traces switching at the same time. There's also some of the full wave solver activity going on to get the via-to-via coupling modeling and non-ideal return path information. So lots of different engines coming together into one space to get you a full model of that entire system. Anyway, so that's power analysis. All right, so let's go ahead and look at the focus of today. That's going into the SERDES analysis. So as you're probably aware, the different types of SERDES technologies have kind of exploded. There's lots of different things to look at, to use to get your information from one point to another. And there's standards with each of these, and it's a challenge for users to go through and figure out how to meet all those standards. And so we want to get in there and try and simplify this as much as possible. So here's some basic questions that you have to go through when you're doing these things. Is the implementation even possible in your system? How much variability can you have on the layout? So often vendors will give you a golden layout structure, but that may not fit your system. So you want to know how much you can vary that. If you don't have the models for the drivers, what can you do? Or you don't even know if the drivers are out yet. What are your options for analyzing your interconnects? How do we quickly validate an interface to a protocol standard? So you know you're doing a PCIe bus. There should be some standards, and there are, as to how that interface should react. So how can you meet up with that? And then getting in these additional 3D features. 3D modeling is very time intensive. There's lots of time involved in generating those models. So you want to speed up the process of generating those, or else it just becomes not worth your time to get into that extra amount of detail. So we want to look into that problem as well. How can I easily find problems in many SerDes channels in my design? So some people may have 50 different differential pairs they got to work with. So how's that going to work out? And looking at hundreds of SerDes lines. All right, so we'll go ahead and jump out now and go look at the HyperLynx tool. The first thing I want to look at is back in the line sim space. So again, this is trying to figure out what's going to work. I have a driver here. It's in a package, and this is a S parameter package model. And then we get down to some traces that supposedly would be on a board, because there's a via structure that it's going to go through, and then another bit of trace, and then another via structure, and then back up to some more packaging, or actually this would be a connector, and then another board, and then a package, and then a receiver. So that's the full interconnect from one chip to another. And we want to look at how these via structures react. So if I double click on this via structure, there's an option here to change this from a basic model. So if we just go through the via visualizer, this is the model we're looking at now. So there is an understanding of two vias side by a certain distance. We know the structure of each of those vias. So we can build a model up of that. But typically with multi-gigahertz channels, we're also putting in some stitching vias, and we're worried about the antipad shape, all these other things that have an effect on the signal. So we want to change this to a 3D model. So we'll switch that over, and to speed this up, I'm going to just grab a model that I've already run through. But let's go ahead and open that up and see what we've got going on here. So we've defined it's a through hole pad stack. So there's a certain pad stack that we've set up before. We can share the anti-pad. We can have some stitching vias in there. You define what layers of stitching vias are going through, how many of there are they, what's the location of those. So some basic parameters. And then this will go off and generate a full 3D model of that structure in the background and generate the S parameter model of that. It takes a little while to do that, but in the end, that'll come back with an S parameter model of that structure. And there's the insertion loss and return loss shown on that. I switch that over to differential. So we can see that at low frequencies, most of the signal is getting through. As it goes higher and higher, there's a little bit of attenuation there. And also low frequencies, there's very little reflection or energy coming back. But as the frequencies go up, we get more and more energy coming back to the input of that structure. But that's just the via. So what we want to do then is look at that via structure, both with and without that turned on. And again, I don't have a lot of time today, so I'm going to just jump straight to the results on that. Give me a second to bring this up. All right, so I've got two different okay, so here are my different models. So I've got no 3D model. So this is this exact structure that we're looking at back here. So one with this as the basic model and one with the 3D model underneath. So this is the return loss, so the amount of energy that's bouncing back. And with no 3D model, that's what it looks like. And then in green, we can see what the 3D model adds. So there is some difference there that model does make. It actually looks a little bit better as far as the amount of energy coming back. So let's switch this over to the insertion loss. And okay, so this is how much energy is getting through with no 3D that's the, okay, so the yellow is no 3D model. So it shows that the amount of energy going through drops by quite a bit, but actually with the 3D model here in blue, you can see it's actually a little bit better. So the basic via model structure that we had didn't include the stitching vias that were helping control the impedance as it went through the power plane. So we can see that is having a positive effect. And then it's a good thing that we did have those stitching vias included in the design. So that's the first thing that we want to go into is increasing our models beforehand. The next thing is what if I don't have driver and receiver models, or I'm trying to figure out whether the structure I'm coming up with is even compliant with the standard. So that's where we have our SERDES Batch Compliance Wizard. And what this will do is I'd come in here and I'd identify the nets that I want to look at and what type of protocol I'm looking at. So if we look in here, we've got Ethernet, OIF, CEI, PCIe, fiber channel, USB 3.1, and JSD. And we're expanding on this. Every release we get more of these protocols in here. This particular one is PCIe, so I can look at the different options under PCIe, look at the 3.0 here. And anyway, so we define the protocol, and we define what the drivers and receivers are. If there's sweeps that I want to do, so after I've run this, maybe it's not quite working, I can come back and change the length or the width of traces and see how that affects it. Same thing with passive components, and change the layer stack up, anything to try and accommodate that. So then we've got the range that we're looking at over. Let me go ahead and run this. And when we're done running this simulation, I'm going to just grab the results here. There we go. This particular simulation takes about 3-4 minutes to run. But when you're done, we get a report back to let you know which ones passed. In this case, they're all passing. We get some additional information on this. So some measurements that were taken against the protocol standards. So that helps you see how well it's fitting within the margins. And then additional information, there are the plots that we can look at. So we can look at the insertion loss plot, near end return, anyway, so various return loss plots and insertion loss plots, some crosstalk ratios. There's also the TDR plot. So this one's interesting if you're not familiar with this. It actually gives you sort of a physical, an impedance plot that kind of reflects the physical structure. So we can see this kind of correlates to the start of the signal coming out of the pads and then going across a long trace and then going through some other structure. We had a connector in the middle there. That's probably this area there, and then another bit of trace that goes along. So one of these at this particular area after the center structure, it's different than the others. So that might be interesting to go back and see why this one in this particular area is different. Anyway, so we get that from that plot, so it's very useful. And the other thing we can get here is, let's see, there's an eye diagram we can pull up for that. Anyway, so a fairly full report on how that's working, and it's quick to get. And the thing I want to mention is it's using our worst case models to just sort of characterize the connection between the two. So even if you don't have the actual models for the driver and receiver yet, you can still run this compliance mode check and verify that, at least according to the standard, your interconnect should work. And we can do the same thing with board sim. So in this case, I've got a couple of differential pairs chosen, and we'll be running this compliance check on the actual routed traces. So same GUI, same interface, only this time we're working with traces that are actually on the board. Then the last one I want to go over is the getting 3D models in the board sim space. So it was easy enough to get that VIA built up back when it didn't exist, just building a hypothetical VIA structure. But now I've got a group of differential pairs, and there's a lot of VIA structures in here that I'm concerned about. So we have this Analyze 3D EM tool to help us look into this. So we'll go ahead and manage the 3D areas. I've already got my bus selected, so it brings those up as the selected nets. The first time I bring this up, there will be no 3D areas. But what I did here was I clicked on this Create Areas for Selected Nets. And that went through and looked at this structure based on a set of parameters that I gave it. And it looked for differential pair structures that met this. So stitching vias and vias and so forth. And it's actually using the HyperLynx DRC engine. I mentioned that it's the rule checker engine that looks at how things are actually built. But it uses that engine to find these structures, and then it goes ahead and creates the area that's going to be turned into 3D structure. So this dotted line indicates the area that's going to be pulled out and turned into an S parameter model. So if I click through here, we've got various different areas that it's chosen for the different nets. The other thing that, well, okay, so once I get all those selected, I can go off and say solve the, the highlighted areas and just select all of these. And I would go off and generate the S parameter models for those. Now, as I mentioned, generating S parameter models, the 3D models, takes a while. These individually, even for a small VIA model, can take half hour to an hour, depending on the complexity. And if I've got 50 differential pairs, I really don't want to do this 50 times. That's a lot of time. So there's an additional button here that says Find Matches for Highlighted Areas. So typically when you're running vias through the board at these high speeds, you will come up with a structure that you like. So look down here, there's kind of a repeated pattern over and over again. So we can tell the tool, look for that pattern, and if you find it, let's just call all those the same and use the same model for each of those, so that I don't have to recreate these S parameter models over and over again. But this particular one, I've gone through and run that, so I do have the S parameter model for that particular section, and it looks like I've got something hooked up incorrectly there. It's probably a 3. No, there we go. It goes from 1 to 4. So the pin numbering can change. But anyway, so that's the amount of energy getting through, and then that's the amount of energy being reflected. So anyway, so I can quickly find the areas, get those mapped around, and reuse that over and over again. Now that becomes part of the simulation. So we'll use the standard transmission lines until we get up to that area. Then they'll switch over to the S parameter model for the VIA structure, and getting that final bit of accuracy so that we more completely match up with what's actually going on. So that is the demonstration part that I wanted to cover. Just finish up with a few extra slides here. Let me just jump to this final slide here. So we had these questions at the beginning. How can you know if the implementation is even possible? We have tools, the line sim, the SERDES Wizard, Protocol Wizard, that let you know whether you're headed down the right path and things are going to work out. How much variability can you have? We have tools to sweep through that. Have an additional 3D Explorer, which works in building those S parameter models in a batch mode. So you can, anyway, more just doing sweeps in the HyperLynx SI tool. What if you don't have models? Well, we mentioned the Protocol Wizard doesn't need the models. We can do that without your models. How do you quickly validate the interface? Well, we got the Protocol Wizards that can do that for you. And then modeling a larger structure or many structures. We've got the 3D Area Manager that we covered here at the end. And then how can you find problems? Well, the HyperLynx DRC tool can be added to the mix. So it's very quick to go through and look for parts of the design that may be a problem, and then from there you can go back and do some analysis from there, or make layout changes before you even get into the analysis stage. So trying to save you time there. And then like I mentioned, the pattern matching for the 3D models. So instead of creating S parameter models for each and every 3D via structure, we just create the few variations that are needed and then replicate that. So, all right, if there's any questions about what you've seen today, or you want to get more information, if you have HyperLynx, I'd suggest you go on our support center and get more information from there. We've got lots of videos and design kits that you can work off of, and we try and keep you informed as new tools come out through this interface. So that's definitely a useful thing to get into if you already are a Mentor customer. If you're new to Mentor, we have on-demand training. So this is training you get access to for a full year. It has videos and labs and virtual computers that you can log into to work off of to get through the labs. And you can go at your own pace. And these are also growing all the time to get you more and more functionality to understand what's going on. So that's all I had for today. Thank you very much for attending. And again, if you do have further questions down the road, contact the people here at Trilogic or myself, Sherwin Davenport. So Sherwin_Davenport at mentor.com. I'm glad to answer any questions, and we can help you learn what you need to know. And thank you for attending today.